Hello, Eugene here. Have you ever had a module where you didn't know what the signals were that were going to it? I've run into that a few times. So what this example is it's going to show how to use the oscilloscope and trace the information, the electronic signals, and retrieve that and decode it with an I2C signal. So this is using an oscilloscope, which makes it very, very handy to get those signals. That way, if you want to create your own program, now you at least have some of the information that you can write your own program with. So here we have the setup where we have the oscilloscope, we have the probes, which are connected up to the I2C TF Luna, and we have a computer program that's also running in the background on the Raspberry Pi. So the first step that we're going to do here is we're going to make sure that our oscilloscope has been reset to the screen, to the display, and also to the internal components. And we do that by pushing storage and default button. Give it about 5 seconds or so and it'll set itself back to its default settings. So on here what we want to do is we want to make it so that the voltage, we want to have this, right now it's set for 1 volt for each vertical section. We want to change that to 2. So on here we look for the vertical and we click to the left, and now this is setting for 2. I'm going to move this upwards. Great, so we only have 1 channel. We're going to have it so that we also put on the second channel, which is our clock. So our clock, we're also going to change this from 1 volt to 2 volts. I'm going to go there. I'm going to move it down just a little bit with this other knob. And great, so now we've got it set, both of these channels set for each one of these increments is 2 volts. We're going to shift the channel a little bit on the screen. So right now the data is in the very, very center. And the way that we do that is we see here we have horizontal. Just by turning this to the left, you can see that this yellow button is moved over. So that's great. We're right there now. So you can see if this is the whole screen, we're right here. So it's about 80% to the left. Here it's about 80% to the left. So everything is looking good there. So now what we want to do is we want to be able to set up the trigger. And the trigger is to automatically record the information when the oscilloscope detects that there's a signal coming in from the computer to the TF Luna from I2C. So what I'm going to do here is I'm going to move the trigger position, and it only shows up when you start to move this knob. So you can see down here it says 440. I'm going to hold it here. All right, so we're going to move that up to 1 volt. Now that we're at 1 volt, that's great. So that means that on a Raspberry Pi, it's usually 3.3 volts that go up. So anything that goes above 1.0, we're going to have the oscilloscope register that as a trigger. The next thing that we want to do is we want to be able to set the parameters for the trigger. So we're going to push over here the trigger section. We're going to push the menu button. So the menu button right now says that we're going to have it so it's going to be on an edge. The source is going to be channel 1, meaning that's where our data is going to be. And we're going to change the slope. So right now this is on the rising edge. We want to change this to the falling edge. So you can either just push the button manually here, or you can use this knob to get to the right section, and then you push inwards to select it. See, it's pretty sensitive, so I have to be really careful on how I do that one. Great, so that one's done. The next thing is we want to make it so that we end up with a single sweep. So right now it's automatic sweep. So let's set this for single. Right now our single light is not lit. When we select single, it automatically sets itself and turns the light on. So now we know that we're set up. So great. Then the next thing that we want to do is we want to set the time base for about 1 second of activity. So right now when you look over here, each one of these horizontal lines is 1 microsecond. We want to change this to about 200 milliseconds. So that way we end up with about a good second worth of data so that we can see it. The way that we do that is we look over here at the horizontal, and we switch it until, just keep turning this knob until this ends up being 200 milliseconds. So that's microseconds. And it'll switch to ms. So that's great. So now we're at milliseconds, 25. We're going to go to 200. Fantastic. That's where we want it. So now that we have this trigger position, we're going to move this over a little bit. Oh, we're going to keep that to 1 volt. There we go. All right. So we should be ready to go now with the single. We've got both channels on. All right, so I'm going to press the button on the computer program to send the I2C signal. When I click on it, we get 163 centimeters. That's an important number that we're going to be actually seeing and going to be decoding on here. You can see that we have these 2 narrow bands where we actually have data, and the rest of this is just noise. So we want to be able to zoom into this data. So the way that we do that, again, is we go back to our horizontal, and we're going to be changing the time. So as we just go into the time, we're going to see here that we have 2 different sets of data. I didn't know that it was going to do that, which is why it's nice to have an oscilloscope. So we're only going to take 1 set of data because it looks like both are the exact same. So we're just going to zoom in to the first one. I'm going to move it over here so we can see it a little bit clearer. Let's see if I do it one more. Yeah, that looks okay. We'll zoom out just a bit here. That's too much there. So now I can see everything there. Now what we want to do is we want to make it so that we can have the oscilloscope decode what this information is. So the way that we do that is we press the math button, and we're going to use the decode. So this is going to decode 1, which is great, decoder, and here it says it's a parallel signal. We want to change this to I2C. So we go down here, again, it's a sensitive one, click on I2C. That's going to change some of the parameters here. So it's good, right now it's presuming that the clock is on channel 1 and the data is on channel 2. That's opposite of what we have. So there's 2 ways of doing this. You can either push this and it'll swap the 2, or you can manually select it and choose the channel that it's connected to. And this one, we're going to change this to channel 1. Great. So now that that's set up, so we have for I2C, the clock is on channel 2, which is the bottom one, and the data is on channel 1. Perfect. So let's actually turn it on. So we're going to turn the decoder on. And on the bottom, you end up seeing that we have some information down here. It's null, and it's not making too much sense here because it's giving us some weird ASCII information. So if you push on this bottom button, it comes up with another menu, and it says the format is in ASCII. We want to change this to hexadecimal or hex. So when we do that, this now changes, and we notice we can't see any of the numbers, they're just dots. That means that there's too much information for the screen size. So what I have to do is I have to zoom in, which we're only going to be able to see part of the data. So if I zoom in and move it to the left, here it's going to say W10, meaning it's writing to the hexadecimal 10 I2C location, and that's on the Raspberry Pi. And we're writing the value 0, and then the TF Luna reports back, we're reading from I2C port 10, and the number coming back is 163, which is exactly the distance that we have shown on the computer. So this is actually the low byte. Then we're going to write to get the high byte. So this is just the way that this one is done. And we're writing 1. So that way we're requesting the high byte information from the TF Luna. And I have to move it over to the left a little bit here so we can see the rest of the data. And here it says we wrote to location 10, we're getting, and we wrote the number 1 to get the high byte. We're reading from location 1 and we're getting the number 0. which is still 163, because if it was above, I think it's 256, or is it 65,535? Anyway, if it gets to be a high enough number, then the high bit starts to get information on there. So that's how we end up taking that. The other part is, what we can do is we can actually add the table. So I'm going to move the vertical, this one, up a little bit more. I'm going to change the position here by pushing that. I'm going to move it up. It's not wanting to do that, so that's okay. We don't have to. What I'm going to do is I'm going to show the event table. I'm going to push this, and the information that we just talked about should be showing. So I'm going to take the event table and turn it on. So now it comes up with a table that is showing that, now it's only showing the information that's on the screen. So I only have the last three bits of information, so it's only showing the last three, meaning it took this amount of time to read to get the value of A3. A3 in hexadecimal is 163 in binary. Same here, we wrote 10 with the value 1, that's to get the high value. Actually, if I go out, I zoom out, there we go. So now it's going to show, again, it's only showing what's on the screen. Here it's going to show that we wrote to address number 10, the value 0 for the low byte, then we read from the value 10, we ended up getting the A3 value hexadecimal, which is 163. When we wrote to get the high bit value to location 10 with the value 1, we wrote back, it wrote back and gave us the value of 0. So this is the way to decode information from the electronics to be able to get I2C information from a TF Luna, and you can use this for whatever I2C communication that you'd like. Thanks for listening, and I hope this helps. Bye now.